Hello, Professor Anupam Yadav.
Can you hear me?
Yes, yes.
Okay, actually there is some firewall issue. Can we start now?
Yes, please.
Okay. Thank you everyone. There was some technical glitch. I welcome you all in this keynote session, and it's my pleasure and privilege to welcome Dr. Swagatam Das. Dr. Swagatam Das is currently serving as an associate professor and head of the Electronics and Communication Services Unit of the prestigious Indian Statistical Institute, Kolkata, India. His research interests include evolutionary computing and machine learning. Dr. Das has published more than 300 research journals and international conferences. He is the founding co-editor-in-chief of Swarm and Evolutionary Computation, an international journal from elsewhere. He has also various journals such as Information Fusion, Progress in Artificial Intelligence, Applied Soft Computing, Engineering Applications of Artificial Intelligence, and Artificial Intelligence Review. Dr. Das has more than 25,000 Google Scholar citations and an H-index of 76 till date now. He has been associated with the international program committees and organizing committees of several reputed international conferences, including New AMVC, IEEE, GECO, Evolutionary Computation, and IEEE Transactions on SMC Part C. He is the recipient of the 2012 Young Engineer Award from the Indian National Academy of Engineering. He is also the recipient of 2015 Thomson Reuters Research Excellence Indian Citation Award as the highest cited researcher from India in engineering and computer science category between 2010 and 14. It is my privilege and pleasure to welcome Dr. Das. Sir, you may please start.
Thank you very much, Professor Anupam Yadav. I also express my gratitude to Professor Keen, Professor Geen, Professor Kusumdeep, and other organizers of this wonderful conference, which is, I think, in its 7th year now. I hope I am audible to all of you. And let me share my screen to start the presentation. Can you see my screen right now in the slides in full screen mode?
Yes, it's not in full mode, but we can see.
Not in full mode. Okay,
yes, not in full mode.
Can you see the slides changing?
No, Dr. Jam, can you confirm also from your end, because I cannot see changing the slides.
Okay, let me share my whole screen in that case. Are the slides now visible?
Yeah, okay. It is visible. Thank you.
Okay. So what I plan to do is, since the time is very less and the content is quite heavy, but very much contextual to the recent developments. So I try to keep the presentation as compact as possible. And then if you wish to drop any offline questions or queries, this email ID is here in the bottom of this beginning slide. And we are going to, in this particular talk for about half an hour, I'm going to explain some very important facets related to the situations under which traditional machine learning algorithms, including the most state-of-the-art deep learning architectures, can actually fail. And that necessitates many auxiliary mechanisms to clean the data, to get the well-behaved data for which most of the machine learning algorithms are actually designed. So class and imbalance is such a scenario which, presents severe challenge to the existing machine learning techniques and tools. we are going to look at it from a broader perspective, and that's how the talk proceeds. So we all know supervised machine learning framework could be expressed in the simplest form through the simplest mathematical equation y equal to f of x. This x is an abstract representation of any object in the form of certain numbers sitting together, forming a feature vector or a feature matrix. This x is the data. What is data? Anything around us which could be abstractly expressed in terms of bits and bytes to a computer qualifies as a data. Okay, so x is the data which goes inside this magic box called prediction function. This is actually the machine learning model. Okay, model is a very favorite term for the statisticians. So f of x is like a factory, like the raw material x goes inside it, and the outcome that it comes out, the finished product that comes out is y. What is y? Y is the numerically encoded class label for the data x. For example, x could be the lung X-ray image of a patient, and y could be 0 if the X-ray shows no sign of pneumonia. Y could be 1 if from the fibrosis pattern in the lung X-ray it is understood that the patient has a bacterial pneumonia, or y could be 2 if x shows, at least the machine learning algorithm discovers that the patient has COVID-19 induced pneumonia. So this function is built on the basis of a number of data items which are labeled by some human expert. This is called the training set. Based on the training set, this machine learning model or the function will be built. And before deploying the function in a practical situation, you must test it with previously unseen data items for which you know the label of the data, but that label is not provided to the machine. That is, such kind of data items are called the test data items. Okay, so this is the whole business. The core of supervised machine learning, also called pattern recognition, goes like this. You have training data. From the training data, you extract the feature vectors. That means you represent each data item in the form of suitable numbers, add labels. These labels are coming from some human expert or supervisors. That's why it's called supervised learning. Then based on this training data, an algorithm is created. Now a new data item comes in, the feature vectors are extracted, and the label must be added. Now, if your algorithm can tell you the correct class label for this new item, then we are very happy. That means the algorithm is doing good. We can deploy it in a practical situation. In most of the cases, machine learning is trying to find a suitable function which maps from, for example, the function I showed you, it maps from the data features into a class label. Similarly, from some X domain to a Y domain. If the output is, continuous, a real number, so that means we are trying to find a functional relation between X and Y. Okay, for example, how the number of credit cards used per household in a posh society depends on the size of the family. Okay, so there is no question of class level. You are trying to learn a function. This problem is called regression. If you want to output a particular class level like class 1, class 2, or class 3, you can output it in the form of such one-hot vectors. Then it is called a classification problem. In other cases, this machine learning model could output a sequence, a matrix, a graph, or tree. In such cases, we call it structured learning. For example, in machine translation, the input could be sentence of some language, maybe Chinese, and the output could be sentence in another language, like English. In speech recognition, the input could be a speech signal and the output could be just a transcription. Chatbots, we know input could be the line typed by some user and output could be a befitting response from the machine. Nowadays, we extrapolate it to matrix valued inputs and outputs. The input could be this sort of an image and the output could be simply a matching real camera clicked image of some structure. Maybe input could be black and white images and output could be such colored images. Input could be a line of text and output could be a picture conjured by the machine matching such line of text. These are all very important and elegant applications of supervised learning for which we require a lot of training data, which must be well behaved and which must reflect adequately the prime characteristics of different classes. So we call it gentleman data. So all the machine learning algorithms are built on the assumption that the training data, the examples that are being shown to the machine, they must be perfect. All the classes, if we are trying to design a classifier, okay, that is the major stakeholder of supervised learning algorithms. So all the classes must be adequately and equally represented in the training set. There should be equal number of representatives from all the classes. Then within a class, if there are multiple variances, multiple varieties, sub-concepts, which are called, so all those sub-concepts must be equally presented. Just for an example, you want to demarcate between apples from oranges, okay? Now within the apple class, there may be red apple, green apple, yellowish red apple, reddish yellow apple, but all are apples. So if you want your machine to well learn the apple class, you should show adequate examples from all such internal varieties or sub-concepts, which is very often missing in training data. All the classes must have similar class conditional distributions. The geometric probability distribution shapes should be similar. If all classes are Gaussian, then it's well and good. Usually, most of the statistical learning algorithms assume such presence of Gaussian underlying distributions. All the features must be defined for all members of the dataset. And number 5, if you see this list, all features must be known for all the data instances. Okay, that means all features must be recorded. We assume, so under these 5 assumptions, the most of the machine learning algorithms work pretty well, but life is hardly so easy. So there are violations of all these assumptions, which we could put through this taxonomy that is called data. Collectively, such violations of these idealistic assumptions are called data irregularities. And data irregularities could be distribution-based, under which we have class imbalance. In the training set, all classes do not have an equal number of representative samples. Some classes are highly underrepresented. Then we have class skew, small disjunct, all the subconcepts within a class are not properly identified. Under the feature-based irregularities, we have missing features. Some features may not have been recorded due to sensing or sensing device failure or equipment failure. We also have absent features where some of the features may be, not defined for some data items. When such data irregularities are there inside your training data, even the most state-of-the-art machine learning algorithms get quite confused, and they simply look like these confused cats. Okay, that's what is going to happen with your algorithm if your data is plagued with data irregularities. And most of the machine learning algorithms are quite affected by one or more such irregularities. Like neural networks are quite sensitive to class imbalance, small disjuncts, absent and missing features, k-nearest neighbors, Bayesian inference. These are all classical machine learning models. Decision trees are inherently immune to feature missingness because they do not use the all features together in the form of a vector. They start building from handful of features selected from the all available one. That's why if some features are missing, they are particularly not affected that way. Coming to the class imbalance problem, the basic problem is inside the training set, one class is greatly outnumbered by representative samples from the other class. Like this red class here, red star class here is the minority class. And the blue class is the majority class. This situation can happen in multi-class scenarios also. Let's take a very practical problem. We did a project with the National Payment Corporation of India long back, and the idea was to every online transaction, if you buy something from Amazon or Flipkart, every such online transaction is stored in a server of some National Payment Corporation. And that transaction is recorded in terms of a number of, features sitting together. It was a 60-dimensional vector. Now, from these transactions